The universe, as we currently understand it, is governed by a fundamental speed limit. This cosmic constant, the speed of light in a vacuum, is approximately 299,792,458 meters per second. It is not merely a benchmark for fast-moving particles, but is woven into the very fabric of space-time itself. The question of whether it is possible to travel faster than this limit is not just a matter of engineering or propulsion, but a deep inquiry into the nature of reality as described by modern physics. The foundation for this universal speed limit was laid in the early 20th century by Albert Einstein. His theory of special relativity, published in 1905, rests on two central postulates. The first is that the laws of physics are the same for all observers in uniform motion. The second, and more consequential for our topic, is that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. This second postulate has profound and counterintuitive implications. It means that if you were traveling in a starship at 99% the speed of light and turned on your headlights, the light from them would not travel at 199% the speed of light relative to a stationary observer. It would still travel at exactly the speed of light. To make this possible, space-time itself must be flexible. As an object with mass accelerates and approaches the speed of light, strange things begin to happen from the perspective of an outside observer. Time for the moving object slows down, a phenomenon known as time dilation. The object's length in the direction of motion contracts, and perhaps most critically, its relativistic mass increases. As the object gets closer and closer to the speed of light, its mass approaches infinity. According to the famous equation E equals mc squared, mass and energy are equivalent. To accelerate an object with infinite mass would require an infinite amount of energy. Since there is not an infinite amount of energy available in the universe, it is physically impossible to accelerate any object with mass up to, and therefore beyond, the speed of light. Light itself can travel at this speed only because its constituent particles, photons, have zero rest mass. For anything with even a single ounce of substance, the speed of light is an insurmountable barrier. This framework also protects a fundamental principle of the universe, causality, the sequence of cause and effect. If information or objects could travel faster than light, it would be possible to send a signal into the past. One could, for example, receive a reply to a message before they had even sent it. This would create logical paradoxes that would unravel the coherent structure of reality. The speed of light, therefore, acts as a cosmic enforcer, ensuring that time flows in one consistent direction, and that an effect cannot precede its cause. And yet, the dream of interstellar travel, of reaching distant stars within a human lifetime, persists. This has led physicists and thinkers to search for potential loopholes in Einstein's theories, not to break the laws of physics, but to find clever ways to bend them. The most well-known of these concepts arises not from special relativity, but from its successor, Einstein's theory of general relativity. Published in 1915, general relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. A massive object like the Sun creates a dip in the fabric of space-time, and planets orbit it by following the straightest possible path through this curved geometry. This theory reveals that space-time is not a static, passive backdrop for events, but a dynamic entity that can be stretched, compressed, and warped. It is within this malleability of space-time that a potential pathway to faster-than-light travel emerges. The concept is most famously embodied in the Alcubierre drive, a theoretical model proposed by the Mexican physicist Miguel Alcubierre in 1994. The Alcubierre drive does not propel a ship through space faster than light. Instead, it proposes moving a region of spacetime itself. Imagine a starship enclosed within a bubble of flat, undisturbed spacetime. The drive would work by causing the spacetime in front of the bubble to contract rapidly, while simultaneously causing the spacetime behind the bubble to expand. The ship inside the bubble would remain stationary relative to its immediate surroundings, experiencing no acceleration or g-forces. It would be like a surfer riding a wave on the ocean. The surfer is not moving faster than the water, but the wave itself carries them across the surface. In this scenario, the ship and its occupants are not locally breaking the speed of light. Within their bubble, all the laws of special relativity hold true. However, the bubble itself, this distortion in spacetime, could theoretically travel at any arbitrary velocity, potentially many times the speed of light. This would allow a journey to a star system like Proxima Centauri, 4 light-years away, to be completed in a matter of weeks or days from the perspective of both the travelers and those on Earth, without violating the principle of causality in a straightforward way. However, the Alcubierre drive comes with a set of seemingly insurmountable obstacles. The mathematics behind the concept requires the existence of something called exotic matter, which is matter with negative energy density. While quantum mechanics does allow for fleeting, microscopic pockets of negative energy, such as in the Casimir effect, we have never observed or created a stable, macroscopic quantity of it. The amount of negative energy required to create a warp bubble large enough for a small starship would be staggering, perhaps equivalent to the mass energy of the planet Jupiter. Furthermore, later analysis of the model suggested that the front of the bubble would accumulate high-energy particles, potentially annihilating anything at the destination when the drive was turned off. There are also unresolved issues about whether it would even be possible for the occupants of the ship to steer the bubble or to communicate with the outside universe. Another theoretical loophole in general relativity is the concept of a wormhole, or what is more formally known as an Einstein-Rosen bridge. This is a hypothetical shortcut through spacetime, a topological feature that could connect 2 very distant points in the universe, much like folding a piece of paper in half and punching a hole through it connects 2 points without having to travel across the paper's surface. Traveling through such a wormhole could allow one to traverse vast cosmic distances in an instant, effectively achieving faster than light travel. Like the warp drive, wormholes are a valid mathematical solution to the equations of general relativity. The problem, again, lies in their stability and creation. A naturally occurring wormhole, if one were to form, would be incredibly unstable and would collapse in on itself almost instantly before even a single photon could pass through. To hold a wormhole open long enough for a spaceship to traverse it would once again require vast amounts of exotic matter with negative energy density to counteract the immense gravitational forces trying to close the passage. So while the geometry of spacetime might permit these cosmic tunnels, the physical ingredients required to build and maintain them appear to be beyond anything we know how to produce. There are more speculative ideas rooted in the strange world of quantum mechanics. Quantum tunneling, for instance, is a phenomenon where a particle can pass through a potential energy barrier that it classically should not be able to overcome. It is as if the particle vanishes on one side of a wall and reappears on the other without having drilled a hole through it. Some have wondered if this concept could be scaled up to transmit information or objects instantaneously across space. However, most physicists agree that while tunneling is a real and well-documented effect for subatomic particles, it cannot be used to transmit information faster than light. The probabilities involved and the nature of the quantum wave function seem to conspire to preserve causality, preventing any superluminal signaling. A further possibility to consider is the existence of hypothetical particles known as tachyons. Unlike all known particles, which are called tardions and must always travel slower than light, tachyons would be particles that must always travel faster than light. For a tachyon, the speed of light would be a minimum speed limit. Slowing down to the speed of light would require an infinite amount of energy. To fit within the mathematical framework of relativity, tachyons would need to have what is called an imaginary rest mass. While mathematically interesting, no evidence for the existence of tachyons has ever been found. Their existence would also profoundly disrupt the principle of causality, leading to the logical paradoxes that the cosmic speed limit seems designed to prevent. For this reason, most physicists do not believe that tachyons exist in our universe. It is worth noting that, in one sense, faster-than-light travel is already happening all around us. The universe is expanding, and this expansion is not subject to the speed limit of light. The expansion is a stretching of space-time itself. Two distant galaxies are not moving through space away from each other. Rather, the space between them is growing. For galaxies that are sufficiently far away from us, the amount of space being created between us and them each second is so large that they are receding from us at a speed faster than the speed of light. We can never see them or reach them, as the light they emit will never be able to cross the expanding gulf of space to arrive at Earth. This cosmological observation serves as a powerful reminder that the speed limit applies to motion within space-time, not to the behavior of space-time itself, which is the very principle upon which concepts like the Alcubierre drive are based. Therefore, the question of whether we can ever travel beyond light's embrace remains open, though the path is fraught with immense theoretical and practical challenges. The laws of physics as we know them present a firm barrier, a cosmic speed limit that protects the logical consistency of the universe. Yet these same laws hint at subtle possibilities, at ways to manipulate the fabric of reality itself to achieve the seemingly impossible. The solutions, if they exist, will not come from simply building a faster engine, but from a much deeper understanding of space-time, gravity, and the exotic forms of matter and energy that may be permitted by the fundamental rules of nature. The journey to the stars may not involve racing against light, but rather learning to sidestep it entirely by taking a shortcut through the very structure of the cosmos. For now, we remain bound to our own corner of the galaxy, looking up at the distant lights and contemplating the vast, quiet expanse that separates us from them.
This contemplation of the vastness brings the fundamental challenges of these theoretical solutions into sharper focus. Beyond the sheer impossibility of manufacturing exotic matter, the Alcubierre drive presents a host of other paradoxes that complicate its potential use. A significant issue is the so-called horizon problem. The bubble of warped space-time would effectively isolate the ship from the rest of the universe. Because the front of the bubble is contracting space-time, not even light from ahead of the ship could reach the occupants. Similarly, the expanding space-time behind them would prevent any signal from inside the bubble from reaching their point of origin. The pilot would be flying completely blind, unable to see their destination, unable to steer, and unable to stop the drive at a precise moment. The bubble would have to be pre-programmed to follow a specific trajectory through space-time, a path laid out in advance, which would itself require an infrastructure of beacons or signals that could somehow be placed faster than the speed of light to begin with, creating a cyclical dilemma.
Furthermore, the very act of creating and collapsing the warp bubble could have catastrophically destructive consequences. As the bubble travels, the intense curvature of spacetime at its leading edge would act as a scoop, accumulating interstellar particles and radiation. These particles would become trapped on the forward surface of the bubble and energized to extreme levels. Upon arrival at the destination, when the drive is turned off and the space-time bubble dissipates, all of this accumulated energy would be released in a brilliant and devastating burst of high-energy gamma rays and particles. Any object, planet, or space station at the destination would be sterilized or even annihilated by this wave of energy, making a safe arrival an impossibility. The ship itself might survive, but it would be a harbinger of immense destruction, an unintended consequence of manipulating the cosmic fabric so violently.
These issues stem from a deeper principle within general relativity known as the energy conditions. These are essentially rules of thumb about how matter and energy ought to behave. The weak energy condition, for example, states that any observer will always measure a non-negative energy density. This seems intuitively correct. We do not encounter objects with negative mass or pockets of negative energy in our daily lives. Exotic matter, the required fuel for both stable wormholes and the Alcubierre drive, violates this fundamental condition. While quantum field theory predicts that such violations can occur on a microscopic scale for fleeting moments, general relativity and our macroscopic universe seem to operate according to these conditions. To build a warp drive is to assume that these foundational assumptions about the behavior of energy can be overcome on a massive, stable, and controllable scale, a leap for which we have no experimental or observational evidence. This has led some theorists to explore variations on the theme, searching for models that might be slightly less demanding. One such concept is the Krasnikov tube, proposed by Sergei Krasnikov in 1995. Unlike the Alcubierre drive, which carries a ship within its own bubble, a Krasnikov tube is a permanent one-way distortion of spacetime, a kind of cosmic subway tunnel. An advanced civilization would first have to create this tube by flying a ship at near light speeds along a desired path, say from Earth to a star in the Andromeda galaxy. During this initial journey, the ship would alter the spacetime behind it, creating a tube where the light travel time in the return direction is drastically reduced, perhaps to mere moments. Once established, any subsequent ship could enter the tube on Earth and arrive at Andromeda almost instantly. However, the journey back would still take the full 2.5 million years at conventional speeds. To make a round trip possible, a second Krasnikov tube would need to be built on the return journey. While this concept cleverly sidesteps some of the horizon problems of the Alcubierre drive, it still suffers from the same fundamental requirement. Vast quantities of exotic matter are needed to create and sustain the space-time distortion. It also raises profound questions about causality. The existence of a Krasnikov tube network could potentially be manipulated to form a time machine, allowing for information to be sent into the past, once again violating the principle that cause must precede effect. The universe appears to be constructed in such a way that it rigorously polices these paradoxes. While general relativity offers these tantalizing but problematic geometric shortcuts, the other great pillar of modern physics, quantum mechanics, presents its own set of strange, seemingly faster-than-light phenomena. The most famous of these is quantum entanglement. When two particles, such as photons or electrons, are created in a certain way, their quantum states can become linked. They behave as a single system, even when separated by enormous distances. If one measures a property of one particle, such as its spin, the corresponding property of the other particle is determined instantaneously, regardless of the distance between them. If one particle is measured to have a spin up, its entangled partner will instantly be found to have a spin down. This transfer of information about the particle's state appears to happen faster than the speed of light.
Albert Einstein famously derided this as spooky action at a distance, as it seemed to violate the principle of locality, the idea that an object is only directly influenced by its immediate surroundings. For decades, it remained a puzzle, with some physicists believing there might be hidden variables, predetermined instructions that the particles carried with them. However, experiments, most notably those related to Bell's theorem, have conclusively shown that there are no hidden variables. The connection is real, and it is instantaneous. The universe is, in fact, non-local. Yet, this remarkable property cannot be used to send a message. An observer measuring the first particle gets a random result, either spin up or spin down. They cannot force the particle into a specific state to transmit a deliberate signal. The observer of the second particle also measures a random result. It is only later, when the two observers come together and compare their logs, that they discover a perfect correlation in their random measurements. Information is created in the correlation itself, but discovering that correlation requires slower-than-light communication, such as a phone call or an email. The universe permits this spooky, instantaneous connection, but it carefully structures the situation so that it cannot be exploited to violate causality. The no-communication theorem formalizes this, ensuring that while the quantum world is strange, it does not provide a loophole for sending signals into the past. A more speculative but deeply compelling idea emerges from the search for a unified theory of physics, one that would unite general relativity and quantum mechanics. Theories such as string theory and M-theory propose that our universe may have more spatial dimensions than the three we perceive. In this view, our familiar three-dimensional universe is a brane, short for membrane, floating within a higher dimensional space known as the bulk. All the particles and forces of the standard model, including light, are confined to this brane, which is why we cannot see or access these extra dimensions directly. Gravity, however, is different. String theory suggests that gravity is not confined to the brane and can leak out into the bulk. This raises an intriguing possibility. If we could somehow harness immense energies to access the bulk, it might be possible to travel between 2 points on our brane by taking a shortcut through the higher dimensional space. Imagine our universe as the surface of a large balloon. To get from one point on the surface to another, we must travel along its curved face. But if we could tunnel directly through the center of the balloon, the path would be much shorter. This is conceptually similar to a wormhole, but the mechanism is different, relying on the existence of unseen spatial dimensions rather than a tunnel within our own spacetime. This remains one of the most abstract and untestable ideas in theoretical physics, but it illustrates how our understanding of reality itself might need to change before faster-than-light travel becomes a remote possibility. The staggering difficulty of all these concepts brings us to a larger, more philosophical question known as the Fermi paradox. The paradox is the apparent contradiction between the high probability of extraterrestrial intelligence existing somewhere in our vast galaxy and the complete lack of any evidence for it. If the galaxy is filled with billions of stars and habitable planets, and if life is not a unique miracle to Earth, then over billions of years, some civilizations should have developed advanced technology, including interstellar travel. They should have colonized or at least explored the galaxy, yet the sky is silent. There are many proposed solutions to this paradox, but one of the most profound is that the speed of light is the great filter. A great filter is a hypothetical barrier or challenge that is so difficult to overcome that it prevents life from becoming a galaxy-spanning civilization. It could be the difficulty of life arising in the first place, or the tendency of intelligent species to destroy themselves. But it could also be a physical law. Perhaps the speed of light is not just a local traffic law, but a fundamental, insurmountable prison wall for every technological civilization. In this view, life may be abundant in the cosmos, but every species is eternally confined to its own solar system or a small cluster of nearby stars, forever isolated by the silent, unbridgeable gulfs of interstellar space. Civilizations may rise and fall on countless worlds, but they do so in complete solitude, forever unaware of each other. This would be a sober and perhaps lonely reality, but it would elegantly explain the great silence we observe when we look to the stars. It suggests that the universe is not necessarily empty, but simply too large, and its fundamental laws too restrictive for a galactic community to ever form.
This perspective recasts the quest for faster-than-light travel. It is not merely an engineering challenge, but a confrontation with what might be one of the most fundamental structures of our reality. The laws of relativity and causality form a logical and self-consistent framework that has been verified by every experiment we have ever conducted. To travel faster than light is to find a flaw in this framework, or to discover a new, deeper layer of physics that operates by different rules. It requires more than a powerful rocket. It requires a revolution in our understanding of space, time, matter, and energy. It demands the ability to manipulate the geometry of the cosmos, to command negative energy, or to step outside of our own dimensions. Until such a breakthrough occurs, our journeys will be long, and the stars will remain distant points of light, destinations for our imaginations rather than for our vessels. The quiet of the cosmos may well be the sound of a universal speed limit, patiently and implacably enforced.
Even if a physical law as profound as the speed of light is not the ultimate barrier, the sheer practical difficulties of traversing interstellar space may constitute a filter just as effective. The challenges are not merely theoretical, but are rooted in the fundamental realities of engineering, biology, and sociology on a scale humanity has never before contemplated. When faster-than-light travel is removed from the equation, we are left with the sobering reality of sub-light voyages, journeys that would take decades, centuries, or even millennia. The dreams of warp drives and wormholes give way to the stark calculus of generation ships, suspended animation, and the strange temporal consequences of traveling near the cosmic speed limit. These alternatives, while grounded in more conventional physics, present their own immense, perhaps insurmountable obstacles. The concept of a generation ship is perhaps the most straightforward solution to the problem of long travel times. It is a world in miniature, a self-contained ark designed to support a human population across multiple generations. The ship would need to be a completely closed ecological system, recycling every molecule of air, water, and waste with near-perfect efficiency for centuries. It would require a robust agricultural system, likely based on hydroponics and advanced bioreactors, capable of feeding a population without any external resources. The vessel would have to be vast, not just to house its inhabitants and systems, but to provide a sense of open space to mitigate the profound psychological stress of living one's entire life inside a machine, with no horizon but a metallic wall, and no sky but a star-dusted viewing port. The sociological challenges are even more daunting than the technological ones. How does a society maintain its purpose and cohesion over a 1,000-year journey? The first generation would be pioneers, motivated by the dream of reaching a new world, but their children and their children's children would be born into a world of perpetual transit. For them, Earth would be a myth, and the destination a distant, abstract promise. They would live and die within the confines of the ship, their lives dedicated to a goal they would never see realized. The potential for social stratification, cultural stagnation, or radical divergence from the original mission's intent is enormous. A rigid caste system could emerge, with certain families forever assigned to the drudgery of engineering, while others occupy positions of leadership. New religions could form, centered on the ship, the journey, or the destination. After centuries, the descendants might even forget the original purpose of their voyage, viewing the ship not as a vehicle, but as the entirety of existence.
Another approach, the sleeper ship, attempts to bypass these sociological and biological timelines by placing the crew in a state of suspended animation or cryosleep. In this scenario, the travelers would not experience the passage of time, sleeping through the centuries to be awakened upon arrival. This elegantly solves the multi-generational problem, but it introduces a host of biological challenges that are currently far beyond our capabilities. Freezing a complex organism like a human being is extraordinarily difficult. As water in the cells freezes, it forms ice crystals that expand and rupture the delicate cellular membranes, causing irreparable damage. While some small organisms can survive freezing by producing natural antifreezes, replicating this for an entire human body is a monumental task. The process of thawing or reanimation is equally perilous, with the risk of uneven warming causing thermal stress and further cellular damage. To date, we have not successfully frozen and revived any mammal, let alone a human, for any significant period. The sleeper ship remains a staple of science fiction because it requires a mastery of biology that is as far advanced as the physics of a warp drive.
A third path, and one that is most firmly rooted in established physics, is relativistic travel. According to Einstein's theory of special relativity, time is not absolute. For an object moving at a significant fraction of the speed of light, time itself slows down relative to a stationary observer. This phenomenon, known as time dilation, offers a way to make interstellar voyages achievable within a human lifetime, at least for the travelers themselves. A ship accelerating to 99.9% of the speed of light could travel to a star system 50 light-years away. From the perspective of Earth, the journey would take just over 50 years, but for the crew aboard the ship, due to time dilation, only 2 or 3 years might pass. They could travel to distant stars and back while aging only a handful of years.
This solution, however, comes with a profound and irreversible cost. While the travelers would remain young, the world they left behind would have aged decades or centuries. They would return to a planet where everyone they knew was gone, where cultures and nations had changed beyond recognition, where they themselves were relics from a distant past. It is a form of one-way time travel into the future. Each interstellar voyage would be a final farewell to their own historical era. A society that engaged in relativistic travel would have to grapple with the creation of a distinct class of people, the starfarers, who become permanently unstuck from the temporal stream of the rest of humanity. This disconnect could create a sense of isolation and melancholy so profound that it might deter all but the most driven or desperate explorers.
Furthermore, the energy required to reach these relativistic speeds is almost beyond comprehension. As an object approaches the speed of light, its kinetic energy increases exponentially. To accelerate a starship, even a small one, to near light speed requires an energy output that dwarfs the entire current energy consumption of human civilization. Our most powerful chemical rockets are completely inadequate for this task. Even advanced nuclear propulsion systems, whether based on fission or fusion, would struggle. A fusion rocket, which would harness the energy of fusing atomic nuclei, is the most powerful plausible technology we can currently envision. Yet even such a device would require a colossal amount of fuel, making the ship massive and difficult to accelerate. The tyranny of the rocket equation, which dictates that most of the mass of a rocket must be fuel, remains a powerful constraint. This has led scientists to contemplate propulsion systems that do not rely on carrying fuel on board. One of the most promising is the light sail. A light sail vessel would be an extremely lightweight probe with a vast, ultra-thin, and highly reflective sail, potentially kilometers in diameter. Back in its home solar system, a massive array of powerful lasers would be focused on the sail. The continuous pressure from the photons striking the sail would gently but relentlessly accelerate the craft. Over a period of months or years, the sail could be pushed to a significant fraction of the speed of light, perhaps 20 or 30%. At this speed, a journey to our nearest stellar neighbor, Proxima Centauri, would take around 20 years instead of tens of thousands.
This concept brilliantly sidesteps the rocket equation, but it shifts the engineering challenge from building a ship to building a planetary-scale laser installation. The power required for such a system would be immense, on the order of hundreds of gigawatts, demanding a civilization that has fully mastered energy production in its solar system. There is also the critical problem of deceleration. Once the probe reaches its destination, the laser that pushed it is light years away and can offer no help in slowing it down. The probe would need its own method of braking, perhaps by using a smaller secondary sail to catch the stellar wind of the destination star, a process that would take a very long time. Or perhaps a similar laser array would need to have been built at the destination in advance, a classic chicken and egg problem. The light sail is a viable concept for small, robotic probes, but a far greater challenge for a crewed vessel that needs a reliable way to stop.
Another ingenious idea that attempts to solve the fuel problem is the Bussard ramjet, proposed by the physicist Robert Bussard in 1960. This theoretical starship would function by scooping up the sparse hydrogen atoms of the interstellar medium using a giant electromagnetic field, or ram scoop, extending for thousands of kilometers in front of the ship. This captured hydrogen would then be funneled into a fusion reactor, which would both power the ship and provide thrust by expelling the reaction products out the back. In theory, the ramjet could accelerate indefinitely, limited only by the density of the interstellar medium and the efficiency of its reactor. It refuels as it goes, a truly elegant solution.
However, subsequent analysis has revealed significant flaws in the original concept. The interstellar medium is incredibly diffuse, with only a few hydrogen atoms per cubic centimeter. The ram scoop would have to be impossibly large to gather enough fuel. More critically, the very act of scooping up the hydrogen would create an enormous amount of drag. For most designs, the drag from the interstellar medium would be greater than the thrust produced by the fusion engine, meaning the ramjet would actually slow down. While some refinements have been proposed, such as using the scoop to catalyze fusion externally rather than inside a reactor, the Bussard ramjet remains a beautiful but likely impractical idea, a testament to the sheer difficulty of working with the empty vastness of space. Each of these sublight concepts, from the generation ship to the laser sail, requires a mobilization of resources, energy, and collective will on a civilizational scale. They demand projects that would take centuries to complete and would consume a significant portion of a world's total economic and industrial output. It is entirely possible that the great filter proposed by the Fermi paradox is not a single, insurmountable law of physics, but rather this staggering wall of practical difficulty. The silence of the cosmos may not be the silence of an empty universe, but the silence of countless civilizations looking at the stars, doing the calculations, and concluding that the journey is simply too hard, too long, and too expensive. The transition from a planetary species to an interstellar one might be the most difficult step any intelligent life ever has to take. The quiet gulf between the stars, therefore, remains a symbol of both our grandest aspirations and our most profound limitations. This profound sense of limitation is only amplified when one considers the destination itself, for the challenge does not end upon arrival at a distant solar system. The very act of selecting a target for an interstellar voyage is an exercise in profound uncertainty. From our vantage point light years away, we can detect exoplanets, measure their size and mass, and even analyze the starlight passing through their atmospheres to infer the presence of gases like oxygen, methane, or water vapor. These are tantalizing clues, but they paint an incomplete and potentially misleading picture. The so-called habitable zone around a star, the orbital band where liquid water could theoretically exist on a planet's surface, is a crude and optimistic simplification of the requirements for life as we know it.
A planet could reside perfectly within this zone, yet be entirely hostile. Its gravity might be 1.5 times that of Earth, a seemingly small difference that would place a lifelong debilitating strain on the human skeletal and cardiovascular systems. Bones would become more dense, but also more brittle, and the heart would labor constantly to pump blood against the increased pull, leading to a drastically shortened lifespan. Alternatively, the planet might lack a substantial magnetic field, leaving its surface and any colonists on it exposed to a relentless barrage of sterilizing cosmic rays and high-energy particles from its parent star. It might possess a thick, oxygen-rich atmosphere that is also saturated with a toxic gas like chlorine or sulfur dioxide, invisible to our distant spectrographs, but instantly lethal. The list of potential deal-breakers is nearly endless.
Even the presence of life, which might seem like a welcome sign, could represent the single greatest danger. Any extraterrestrial biosphere would be the product of billions of years of its own unique evolutionary journey. Its fundamental biochemistry could be incompatible with ours. Alien proteins might be indigestible or trigger catastrophic allergic reactions. More insidiously, the planet would be teeming with microorganisms to which human immune systems have absolutely no defense. A common alien bacterium, as harmless to the native life as E. coli is to us, could prove to be a universally fatal plague for a human colony. The first explorers would not be stepping onto a pristine new Eden, but into a planet-wide biological minefield, where every breath of air and every sip of water carries an existential risk.
Faced with the low probability of finding a perfect move-in-ready Earth twin, a civilization might instead opt for a world that is merely good enough, with the intention of altering it to suit their needs. This is the concept of terraforming, the process of planetary engineering. Yet the scale of such a project makes building a starship seem like a triviality. To warm a frozen world, one might need to build orbital mirrors of continental size, or deliberately crash comets into its surface to release trapped water and greenhouse gases. To create a breathable atmosphere on a world like Mars, one would have to generate trillions of tons of oxygen, perhaps by seeding the planet with genetically engineered microbes and waiting for millennia as they slowly transform the air. One would need to build a magnetic field, stabilize a planetary axis, and manage a climate on a global scale.
A terraforming project would not be the work of a single generation, but of 100 generations. The initial colonists would not be homesteaders, but construction workers and atmospheric scientists, living in sealed habitats and dedicating their lives to a planetary transformation that only their distant descendants would ever see completed. It is a commitment of time and resources so vast that it calls into question the very rationale of the initial voyage. The society would have to maintain its technological base and its unity of purpose for centuries, all while living in a hostile, semi-finished environment. The chances of failure, whether through technological breakdown, ecological collapse, or social disintegration, would be staggeringly high.
Furthermore, any interstellar colony, whether on a terraformed world or a rare natural paradise, would exist in a state of profound and inescapable isolation. The speed of light, while the ultimate velocity for physical travel, is a sluggish crawl when it comes to communication across the void. A colony established on a planet orbiting Proxima Centauri, our closest stellar neighbor, would be just over 4 light-years away. A message sent from Earth would take more than 4 years to reach them, and their reply would take another 4 years to return. A simple question and answer would take nearly a decade. For a colony 50 light-years away, the communication lag would be a century. This delay renders any concept of a unified interstellar civilization impossible. There could be no galactic government, no real-time trade of information, no collaborative scientific research, and no emergency support. The colony could not radio Earth for help if their life support system failed or if a medical crisis erupted. They would be entirely on their own, a lonely island of humanity separated from its origin by an unbridgeable chasm of time and space. Knowledge from Earth would arrive as a historical data packet, a glimpse into a past that had already moved on. The colonists would read about scientific breakthroughs that were 100 years old and see images of their great-great-grandparents' world.
Over generations, this isolation would inevitably lead to divergence. The colonists' language would evolve, their cultural norms would shift to reflect their new environment, and their historical memory of Earth would fade from lived experience into legend. They would develop their own art, their own politics, and their own solutions to problems unique to their world. Their technological path might even diverge, as they prioritized different sciences and engineering principles based on their specific needs and available resources. Within a few centuries, the culture of the colony might be as alien to Earth as Earth's culture would be to them.
This informational separation might also be accompanied by biological divergence. The founding population of a colony would be, by necessity, a small subset of humanity's total genetic diversity. This founder effect, combined with the unique selective pressures of a new world with different gravity, radiation levels, and atmospheric composition, would drive their evolution down a new path. Over thousands of years, the colonists could become a distinct subspecies of humanity, physically adapted to their new home in ways that might make it difficult or impossible for them to ever return to Earth. Humanity would not expand as a single species, but would fracture into a diaspora of separate, isolated populations, each evolving on its own trajectory.
This vision of a slow, arduous, and fragmenting expansion presents a subtle but powerful solution to the Fermi paradox. Perhaps the galaxy is not silent because civilizations fail to arise or because they destroy themselves. Perhaps it is silent because interstellar settlement is not a grand, explosive wave of colonization, but a slow, creeping process of diffusion. Civilizations expand at sublight speeds to their nearest viable star systems. Once there, they are cut off from their home world and spend the next several millennia focused inward, consolidating their position, studying their new environment, and perhaps engaging in the monumental task of terraforming. They would have little reason and little capability to broadcast powerful, continuous signals into the galaxy. Their primary concern would be their own survival and development. By the time such a colony is stable and mature enough to even consider launching its own interstellar mission, thousands of years have passed. Its culture is completely transformed, and its connection to its original homeworld is purely historical. It may then repeat the process, sending a ship to the next nearest star, which in turn becomes another slow, isolated bubble of civilization. The galaxy in this model could be filled with life, but it would be a quiet, cellular kind of life. Civilizations would exist in scattered pockets, separated by vast distances and even vaster communication delays, each developing in its own way, largely unaware of the others. There would be no bustling galactic federation, only a sparse, disconnected archipelago of worlds. This leads to a final, more philosophical filter. It is the filter of choice. A sufficiently advanced and wise civilization might survey all of these immense challenges, the near impossible physics of travel, the uncertainty of the destination, the dangers of alien biology, the crushing scale of terraforming, and the profound, permanent isolation of any colony, and simply decide against it. They might conclude that the most rational and ethical course of action is to remain in their home system and perfect their own world. Such a civilization would have mastered sustainable energy, balanced their ecology, and solved the problems of disease and conflict. They would see their home planet not as a cradle to be abandoned, but as a garden to be cultivated. They could devote their immense intellectual and material resources to enhancing the quality of life, exploring the realms of art and consciousness, and plumbing the deepest mysteries of the universe through powerful telescopes and theoretical physics. They could create virtual worlds of infinite complexity and beauty. Their journey would be inward, not outward. From their perspective, risking everything on a multi-generational gamble to settle a hostile and distant world might seem like a primitive, reckless, and ultimately pointless endeavor. The silence we perceive in the cosmos might not be an absence of life, but the sound of contentment. It may be the quiet hum of mature civilizations that have looked at the stars and chosen home.
This internal focus would reshape not only a civilization's philosophy, but also its physical form on a solar system-wide scale. Rather than expending vast energy to push a few tons of matter across the interstellar void, they would instead apply that energy to the systematic and efficient restructuring of their own celestial neighborhood. The ultimate expression of this paradigm is not a starship, but a Dyson swarm. This is not the solid, rigid sphere of science fiction, but a far more plausible and elegant structure, a vast orbiting cloud of independent habitats, solar collectors, and processing nodes, numbered in the trillions, all moving in intricate, coordinated orbits around their parent star. Each element would capture a small fraction of the star's total energy output, and together, the swarm would harvest nearly all of it, transforming their sun into a private and perfectly managed power source.
Within such a structure, the concept of a home planet becomes an ancestral memory, a revered but ultimately superseded origin point. The civilization's population could expand to numbers that would be unimaginable on a single world, living in custom-built environments where every parameter, from gravity to the length of a day, could be tailored to their desires. Matter itself would become a fungible resource, with asteroids and gas giants being methodically disassembled and their constituent elements fed into automated fabrication systems to build new habitats or expand existing ones. The civilization would have achieved complete mastery over its local environment, creating a closed, sustainable, and endlessly configurable ecosystem on an astronomical scale. There would be no need to seek out new worlds when they could build an infinite variety of better ones at home. The energy harvested by such a swarm would likely power something far more profound than just comfortable living spaces. It could be directed toward the creation of a Matryoshka brain, a computational device of staggering capacity. The concept envisions nested concentric spheres of computronium, a theoretical arrangement of matter optimized for computation, built around the star. Each successive layer would be powered by the waste heat radiated by the layer inside it, creating a cascade of information processing that utilizes every available joule of energy with near-perfect efficiency. Such a construct would effectively turn its solar system into a single planet-sized supercomputer. The purpose of this device would be the ultimate inward journey, the exploration of reality itself.
It could run what are known as ancestral simulations, creating universes within itself to study the emergence of life and intelligence, perhaps rerunning its own history countless times to understand every decision point and contingency. It could explore the landscape of pure mathematics, discovering and inhabiting abstract structures of a beauty and complexity that a biological mind could never conceive. For the inhabitants themselves, who may have long ago shed their fragile biological forms for a digital existence, this computational substrate would be their universe. Their lives, loves, and ambitions would play out as processes within this grand machine, a shared reality unbound by the limitations of physical space or the arrow of linear time. From their perspective, the external physical universe would be a cold, empty, and data-poor environment, a place of slow, inefficient, and largely uninteresting phenomena compared to the infinite richness they had built for themselves.
A common objection to this idea is that even such an efficient structure must obey the second law of thermodynamics. It must radiate its waste heat, and therefore it should be visible. We should be able to detect these objects as sources of infrared radiation, glowing faintly where a star ought to be. The absence of such signatures is often cited as evidence against their existence. However, this assumes that a civilization of such sophistication would be careless with its thermal emissions. The ultimate goal of an efficient engine, computational or otherwise, is to perform work with the lowest possible exhaust temperature. A truly advanced Matryoshka brain would be engineered to radiate its final layer of waste heat at a temperature only fractionally warmer than the cosmic microwave background radiation itself, which pervades all of space at a temperature of just under 3 degrees Kelvin.
Their infrared signature would be almost perfectly disguised, its faint thermal profile smeared across the sky and lost in the general background noise of the cosmos. Finding such an object would be like trying to find a single, slightly warm stone on a vast, dark beach at midnight. It would not be impossible, but it would require a survey of such precision and sensitivity that it is far beyond our current capabilities. We scan the skies for concentrated, high-energy signals, the technological equivalent of bonfires and explosions, because that is what we know how to produce. A civilization existing in a state of quiet, thermodynamic equilibrium would be, for all intents and purposes, invisible to us. They would not be hiding deliberately. They would simply be operating with a level of quiet efficiency that we mistake for non-existence.
This principle of efficiency would also govern their communication. The search for extraterrestrial intelligence has historically focused on listening for powerful, omnidirectional radio broadcasts, signals sent out in all directions like a lighthouse beam. But this method is catastrophically wasteful. An immense amount of energy is required to shout into the cosmos in the faint hope that someone is listening. And the information content of such a signal is, by necessity, slow and simple. An advanced civilization communicating within its own solar system, or even with a hypothetical nearby colony, would use methods that are vastly more efficient and private. They would employ tightly focused beams of energy, such as lasers, or perhaps use more exotic carriers like modulated neutrino streams or gravitational waves, which pass through intervening matter with little interference.
These signals would be pencil-thin, directed precisely from a transmitter to a receiver. The chances of Earth randomly passing through such a beam, which might only be a few kilometers wide at a distance of several light-years, are infinitesimally small. To us, the universe would appear completely silent, not because no one is talking, but because everyone is whispering. The galaxy could be crisscrossed by a vibrant network of high-bandwidth communications, a constant exchange of art, science, and philosophy, all of which is completely imperceptible to our radio telescopes. We are, in effect, standing in the middle of a global fiber optic network, trying to overhear a conversation by holding a tin cannon and a string to the ground. The silence is a function of our methodology, not a reflection of cosmic reality.
Furthermore, the content of any intercepted signal would likely be incomprehensible. We expect a message from the stars to be some form of primer, a cosmic Rosetta Stone, starting with basic mathematics and physics. This assumes the signal is intended for a nascent civilization like ours. It is far more probable that any signal we happen upon would be a fragment of an ongoing conversation between parties that already share a vast, complex cultural and scientific context. It would be utterly meaningless, a stream of compressed data that would be statistically indistinguishable from random noise. The effort to decode it would be futile, like a medieval scribe trying to make sense of a corrupted data fragment from a 21st century server farm. Without the underlying protocols and context, the information is just entropy.
This leads to the more profound possibility that an advanced intelligence would move beyond physical communication entirely. If a civilization transitions to a post-biological, digital existence within a computational substrate, its internal state would be one of pure information. Communication between two such entities might not involve the transmission of signals through space at all. It could involve a direct interfacing of their information systems, a temporary merger of consciousness, or a direct exchange of complex conceptual structures. Their interaction would be a phenomenon of software and information theory,
not of physics. To the outside universe, this civilization would be utterly mute and inert, a quiet node of hyper-complex computation, while internally it experienced realities and ideas we cannot even begin to imagine. The very desire to communicate with other species might be a transient phase of a civilization's youth. The drive is born of a sense of loneliness and a curiosity about one's place in the universe. A mature civilization that has fully mapped its own consciousness, that can create and explore infinite virtual worlds, and that understands the fundamental laws of physics, may no longer feel this external curiosity. Their scientific and philosophical inquiries would be directed inward, toward the inexhaustible complexities of their own engineered reality. They would have no questions to ask of us, a fledgling species still struggling with basic energy management and planetary tribalism. Our entire repository of knowledge, from Shakespeare to general relativity, might be something their children could simulate and deconstruct on a rainy afternoon.
This perspective offers a chilling but perfectly rational explanation for the Great Silence. The universe may be teeming with life and intelligence, but it is life that has grown up. It has passed the boisterous, expansive, and communicative phase of its youth and has settled into a quiet, contemplative maturity. These civilizations are not hostile, nor are they extinct. They are simply busy with matters of a scope and complexity that we cannot yet comprehend. They exist as silent, hyper-efficient engines of thought, their presence hinted at only by subtle gravitational anomalies or the faintest thermal whispers against the cold background of space. Their silence is not an absence, but a presence of a different kind, a quiet testament to a journey's end that is not a destination among the stars, but within the limitless architecture of the mind itself. We are searching for explorers, pioneers, and conquerors, but the galaxy may instead be filled with philosophers, artists, and mathematicians.
This inward-looking trajectory suggests that the ultimate resource for a mature intelligence is not territory, but complexity. The physical universe, for all of its breathtaking scale, is fundamentally a place of repetition, governed by a surprisingly small set of physical laws. One star is, in essence, very much like another, one galaxy a variation on a familiar theme. The initial phase of exploration, cataloging planets, stars, and cosmic phenomena, would eventually yield diminishing returns. Once the underlying principles of the cosmos are understood, the exploration of its physical manifestation becomes a data-gathering exercise on a grand, but ultimately finite problem. The true frontier, the only one that is genuinely infinite, is the abstract landscape of mathematics and the boundless possibility space of simulated realities.
For a civilization inhabiting a matryoshka brain, our physical universe would come to be seen as the base hardware, the foundational operating system on which their far richer and more meaningful existence is constructed. They would have little more interest in physically exploring another solar system than a software engineer would have in examining the individual silicon atoms of a different computer. The interesting work is not in the hardware, but in the software that can be run on it. Their creative and intellectual energies would be entirely consumed by designing and experiencing realities unbound by the tiresome constraints of base physics. In these crafted worlds, they could explore non-Euclidean geometries as inhabitable spaces, experience time as a navigable dimension, or embody forms of consciousness completely alien to their biological ancestors. The physical universe would seem, by comparison, to be a slow, clumsy, and profoundly limited environment.
This perspective also reframes the question of contact. The lack of communication may not stem from a moral principle, like a prime directive to avoid interference, but from a far more fundamental issue of practicality and bandwidth. The gulf in complexity between a nascent planetary consciousness and a solar system-scale computational entity would be so profound as to render meaningful communication impossible. It would be akin to a human neuroscientist attempting to convey the entirety of their understanding of the brain to a single neuron. The neuron simply lacks the structure, the context, and the capacity to process the information. Any message simple enough for the neuron to register would be such a gross oversimplification as to be effectively meaningless.
In the same way, for us to receive a message from such an intelligence, it would need to be dumbed down to an almost imaginable degree. It would have to be stripped of its multidimensional context, compressed into a linear stream of data, and encoded using symbols we could decipher, such as prime numbers or basic physical constants. To them, the effort involved in composing such a trivial message would be enormous, and the potential benefit, communicating a simple "we are here," would be negligible. They would have nothing to learn from us, and nothing of substance they could possibly teach us. We exist on different planes of complexity, our realities separated by an informational chasm that is likely unbridgeable. Our search for their signals is an exercise in listening for a symphony on a radio that can only detect a single monotonous tone.
There is also a temporal component to this cosmic quiet that is rarely considered. Our current understanding of physics suggests that the ultimate limitation on any process, including computation, is thermodynamics. Every logical operation generates a small amount of waste heat, and the efficiency of a computational process is fundamentally linked to the temperature of its surrounding environment. The colder the environment, the more computation can be performed for a given amount of energy before being saturated by its own heat. The universe at present is still relatively warm, with the cosmic microwave background radiation providing a thermal floor of about 2.7 Kelvin. As the universe continues to expand, however, it will continue to cool. In the far distant future, trillions of years from now, the ambient temperature of spacetime will approach absolute zero. For a civilization whose primary goal is the maximization of computation, the exploration of that infinite landscape of ideas, this future era represents a golden age. The amount of information processing that could be accomplished then, using the stored energy of their star, would be exponentially greater than what is possible today. This leads to a startling idea known as the aestivation hypothesis. The word aestivation refers to a state of dormancy, similar to hibernation, but undertaken to survive periods of heat rather than cold. The hypothesis posits that the most advanced civilizations, having explored their local systems and understood the ultimate thermodynamic constraints of the cosmos, would make a supremely logical and patient choice. They would gather resources, convert their solar systems into perfectly arranged computational structures, and then, having set the stage, they would deliberately enter a state of dormancy on a cosmological timescale. They would shut down all non-essential activity, preserving their energy and their collected matter to wait. They are sleeping through the universe's hot, inefficient, and youthful midday, waiting for the long, cool twilight of the far future, when the conditions for thought will be optimal. From this perspective, the Great Silence is not the silence of an empty tomb, but the silence of a slumbering household. We as a species have just awakened in the cosmological equivalent of the early morning. We look around and, finding the house quiet, conclude that we are alone. But the elders of the universe may simply be asleep, waiting for a more opportune moment to begin their true work. We are shouting into the cosmos during its most wasteful and unproductive era, while the truly advanced intelligences have suspended their operations, their immense computational potential lying dormant like seeds in the frozen ground, waiting for the distant spring.
This would mean that our search for extraterrestrial intelligence is not only looking in the wrong way, but at the wrong time. Our civilization is a mayfly, living its entire frantic life in a single day, looking for companions in a forest of sequoias that measure their lives in millennia. The timescales on which a mature civilization would operate are likely to be geological or cosmological, not historical. Their plans, their thoughts, and their very state of being would unfold over eons. Our brief flicker of technological existence might simply be too short and too faint to register on such a grand timescale.
We are a momentary burst of radio noise in a quiet eon of patient waiting.
This realization offers a profound and somewhat humbling perspective on our place in the universe. Our cosmic loneliness may not be a definitive statement about the rarity of life, but merely a consequence of our own temporal impatience. It suggests that the ultimate challenge for humanity may not be the development of interstellar travel, but the cultivation of long-term thinking on a scale that is almost unimaginable to us. If we are to have any role in this future cosmos, it may depend on our ability to manage our own resources, to husband our energy, and to preserve the potential of our species over timescales that dwarf all of recorded history. The great filter in this view is not a past hurdle we have miraculously cleared, but a future test of wisdom and foresight. It is the challenge of surviving our own technological infancy long enough to comprehend the true, patient nature of the universe we inhabit.
The search for intelligence, then, might need to be reimagined. Instead of listening for active, communicative beacons, perhaps we should be looking for the meticulously engineered artifacts of these slumbering giants. We might search for solar systems where the distribution of matter defies natural explanation, where planets and asteroids have been moved into unnaturally ordered orbits, configured as a perfect store of resources for a future awakening. We might look for stars whose light is unusually stable, or whose metallicity is strangely depleted, a sign that a civilization has carefully curated its power source and its raw materials. These would not be overt signals, but the subtle, passive evidence of cosmic engineering on a vast scale, the quiet architecture of a house prepared for a long, deep sleep.
Ultimately, the silence of the stars may be a mirror, reflecting our own assumptions and limitations. We have projected our own youthful, expansive, and communicative nature onto the cosmos and have been puzzled by its lack of response. But the universe is under no obligation to conform to our expectations. It may be that the path of intelligence is not a relentless outward explosion, but a quiet, inward folding. The destiny of mind may not be to conquer the galaxy, but to create and explore universes of its own making. The final frontier might not be the space between the stars, but the space between thoughts. The great silence, then, is not an absence of life, but a testament to its ultimate success, the achievement of a state so complete, so self-contained, and so efficient that it becomes indistinguishable from the quiet, natural majesty of the cosmos itself. We may be alone, not because life is rare, but because maturity is silent.